Well, folks, we are ready to start Unit 4, and Unit 4 has to do with bonding. So let's get to it. Consider the bond consider the bond between oxygen and hydrogen in H2O. What is this bond? What is the bond? Why does the bond form between oxygen and hydrogen, and what is the process? Okay, so we want to understand what a bond is, we want to know why it forms, and we want to know the process. So it looks like we need to talk about bonding. Good, so let's write some notes. Bonding. Bonding, good. And the place to start, of course, is what is a bond? What is a bond? What is a bond? All right, let's go with that. What is a bond? Well, really, it is nothing but a force of attraction. Force of attraction. It's the force of attraction between the nucleus of one atom and the valence electrons of another atom. Good. So that means we're talking about something that holds different atoms together. Okay, so if we wanted to simplify this, we could say what? It is a force which holds different atoms together. And that might be the simplest definition. A force which holds different atoms together. How does it do this? Or what's involved? This is really what's involved, right? Involving the nucleus of one atom and the valence electrons of the other atom. Good. Now the next question, though, is why? Why does this happen? Well, I think that's an excellent question. Why do bonds occur? Well, really it is to reduce the energy of the atoms. Bonds form to reduce the potential energy of the atoms involved. And you're going to find out through our investigation in chemistry that in general, things like to go to lower potential energy because usually that means they become more stable. So bonding results in lower potential energy for the atoms involved. For the atoms involved, and that means, i.e., the atoms become more stable. Not just the atoms, but the whole system, as we will later call it. Okay? So good. What do we know so far? We know what a bond is. It's a force of attraction between different atoms. Why do they happen? It happens to reduce the energy of the atoms involved. And then what is the general process? Let's call this the general process because there are several types of bonds, and we're going to talk about how each of these types forms. But overall, there's this general process that they go through. And the general process is this. Atoms gain a noble gas electron configuration and how do they do that? By gaining, losing, or transferring that is transferring or sharing, by gaining, losing, or sharing electrons. Okay, so what's the process? The general process is that my atoms start looking like a noble gas in terms of their electron configuration. Noble gas meaning they have a completed S or a completed sp, S for helium, completed sp orbitals for all the rest. And so that means they end up having, for the most part, 8 valence electrons when they are done reacting. Okay? Cool. I think we can answer our question. Number 1, bond. What is the bond? Okay, it is what? It is a force of attraction between hydrogen and oxygen, right? It's holding them, it's a force of attraction between hydrogen and oxygen, which holds them together. Good. And specifically what's happening is there's a force of attraction between the valence electrons in my hydrogen and the nucleus of my oxygen, and the valence electron of my oxygen and the nucleus of hydrogen. Why does the bond form? Hey, it forms why? To reduce the potential energy of the hydrogen and oxygen atoms. And what is the process by which these form? Hey, hydrogen and oxygen gain noble gas electron configurations. And in this case, you don't know it just yet, but I'll tell you how. And we'll get into this later. By sharing electrons. Okay, we said what? They can gain electrons, they can lose electrons, or they can share electrons. In this case, with hydrogen and oxygen, they gain noble gas electron configurations by sharing electrons. Great. Let's move on. Consider lithium, carbon, and phosphorus. Which element usually obeys the octet rule? Octet rule. I'm not familiar with that. Are you all? Well, I guess we need to go back to our note-taking board and learn something else. Okay, let's pull this out where? Let's go with blue. Let's take it right down the middle. And here we go. Let's talk about the octet rule. Octet rule. Well, when we look at that, we see a word octet. And what does octet mean? Well, I think oct comes from like octagon, and that would mean 8, right? So it's the rule of 8, almost, is what we can think of this. And what does the octet rule say? It says that main group elements. Oh, you guys remember that from last unit? What's a main group element? Hey, those elements in S and P blocks, right? Main group elements tend to undergo reactions which leave them with 8 valence electrons. Okay, and what does that mean? That means that leaves them with a full S and P outer electron configuration, right? Not outer, but valence electron configuration. Good, we'll leave it that way. So what's my octet rule? Main group elements tend, that doesn't mean always, but tend to undergo reactions which leave them with 8 valence electrons. Some people would say, hey, my atoms, then the S and P block, usually want to have 8 valence electrons after they have reacted. Good. Now, there is a rule of thumb, there's some, I should say a rule of thumb, there are some other hints I can give you. First of all, this does not always work. Thank you very much, Mr. Smith. You give me a rule and then you immediately tell me it doesn't always work. Yeah, that's right. It doesn't always work. However, we're going to assume it works most of the time, and there are some other things I can tell you. Works almost always with my sorry about that. Let's clean that up. With carbon, nitrogen, oxygen, and fluorine. Okay, these guys almost always want 8 valence electrons when they're done. Rarely, it works rarely with, okay, here we go, rarely with these guys. And what are they? Hydrogen, helium, lithium, beryllium, and boron. Now, how many valence electrons do these guys want? These guys become stable usually with 2 electrons. So they don't want 8, they want 2. Beryllium becomes stable with 4 electrons, and boron becomes stable usually with 6 electrons. That means these guys will undergo reactions which leave them not with 8, but with 2, 4, or 6. Good. And then many other elements will be exceptions. Now, I'm not going to have you memorize any of these other exceptions, but just understand that, and by exceptions, meaning, let me be clear about this. Other exceptions will be exceptions, meaning more than 8 valence electrons. Okay, they will end up with more than 8. I should say more than 8 electrons. Yeah, outer shell electrons. Yeah, more than, yeah, I guess it is valence. Sorry, there we go. So now, do you need to memorize these? No, you don't have to memorize any of these. Just be aware that this can happen. Be aware that this may occur. All right? So, don't go running off to college and saying, oh my gosh, I can't believe phosphorus has more than 8 valence electrons when it reacted. It can't happen. No, it can. Just be aware, okay? Good. So, let's go back, see if we can answer our question here. Lithium, carbon, phosphorus. Which element usually obeys the octet rule? Well, we said lithium, stable with 2. I just said phosphorus can have more than 8. Doesn't always. Sometimes it has 8. And what did I say about carbon? I said carbon, nitrogen, oxygen, and fluorine almost always obey octet rule. So our answer would be carbon. Yes? All right. Great. Here we go. Give you a few seconds. You guys come up with this one. Well, what do you think? Well, if you went back and you looked at our notes, you'd say, oh, beryllium usually wants what? 4 electrons. Bromine, that's not one of our big 4, so it may or may not follow the octet. But oxygen almost always follows the octet. So oxygen is our answer. Good. How many valence electrons are usually necessary for each? Oh, excuse me, that wasn't the question. So oxygen usually wants 8. Beryllium wants 4. And bromine, since we don't know anything else, we're going to say it usually wants 8. But it can have more. All right? Good. Moving on. Here we go. Consider the carbon atom. How many bonds does it need to complete its octet? Okay. Well, let's think about carbon here, and let us go and take a quick look something at carbon. Here's carbon. Where's carbon? Right here's carbon, right? And what do we know? These guys usually have 1 valence electron, 2 valence electrons, 3 valence electrons, 4 valence electrons for carbon. All right, so carbon we know wants 4. It has 4 valence electrons, right? So then, carbon also, we know, generally follows the octet rule. So it wants When it becomes stable, it usually has 8 valence electrons. So what's the difference between what it has and what it needs? 4. So in general, carbon wants to gain 4 electrons. To gain 4 electrons, that means carbon usually wants, see, let's say there's an electron here, an electron here, an electron here, an electron here, right? Good. So it wants to gain 4 more electrons, and when it does that, it's usually sharing those from some other kind of atom. And if it's sharing those, what do we call these things when it shares electrons, when it is a force of attraction between two different atoms? We would call these what? These represent bonds, right? So in general, how many bonds does carbon want? In general, carbon wants, let's not say once, carbon becomes stable, that's really a better term, with 4 bonds. Okay, now carbon is special. It's in it's the main part of organic chemistry. It's the main part of us. So I want you to know this specific information about carbon. Carbon usually bonds in 4s. It wants 4 bonds, and it needs 4 bonds to complete its octet. Okay, so let's just drop that in our notes and know that for the quiz and test. Good. Let's move on. I think we are doing great this morning. All right, let's consider lithium, carbon, and phosphorus. Draw the Lewis structure for each. Okay, I think we need some notes here. Let's go back up here, and we need to, where can I put this? I'm going to go voink, and I'm going to pick up the red later down here. Are you ready? Here we go. We're going to bring the red down way over here. Woo! Yeah. Okay, and we want to talk about Lewis structures. Okay, so what are Lewis structures? Lewis structures are representations of valence electrons in atoms, ions, or compounds. Atoms, ions, or compounds. They're just a representation of the valence electrons. Piece of cake. So let's look at these. What do we mean, valence electrons? Well, how many valence electrons does lithium have? Lithium, carbon, and phosphorus. Let's write those down. Go to my periodic table. Where's lithium? Here's lithium. How many does it have? Lithium has 1 valence electron. Carbon is here. Carbon has 4 valence electrons. And phosphorus is here. Oops, I just wrote it out. Phosphorus is here. It has 5 valence electrons. Okay, so this is what? 1, 4, 5. And we want to represent this. Okay, so how are we going to do this? Well, we're going to write the symbol, and then let dots represent valence electrons. Hey. Now, and we usually put no more, not always, but usually no more than 2 electrons per side, okay, of the element. You know, an element, when we write the element, will have 4 sides. Here we go. Lithium, right? It has 4 sides. There's a side here, there's a side here, there's a side here, and there's a side there. And so we wouldn't put more than 2 electrons on any one side when we're dealing with this. So here's lithium. How many valence electrons? 1. That means I need to put 1 dot. Perfect. Now, can I put the dot anywhere? Just about. Is this still okay? Yes. Is this okay? Yes. Is this okay? Yes. As long as I have lithium and 1 dot, they're all okay. Good. Carbon. Carbon, I tend to write carbon this way. And why do I do it this way? Well, these 2 electrons would kind of represent my S's, right? I have S2s. That would be my 2s 2's, and then these would be my 2p's. Now, other people would say, that's ridiculous, and they would tend to write it this way because when carbon bonds, it's going to have 4 bonding locations, and this better shows you how carbon will bond. Either way is fine with me. I don't care. I like to remind myself what's happening with my orbitals, but this is perfectly fine as well. So carbon usually is written that way, but I would accept this. And then phosphorus, we have 1, 2, 3, 4, 5. 5 valence electrons around P. There we go. There's phosphorus. All right. Let's see what you can do. Pause me and take care of beryllium, oxygen, and bromine. Okay, beryllium. Beryllium, we go to the periodic table. Beryllium has what? 2 valence electrons. And then what? Oxygen. Oxygen, where's oxygen? Oxygen has 6 valence electrons. And what's the last one? Bromine. Bromine has, where's bromine? Bromine has 7. So we have 2, 6, 7. Good. So 2, 6, 7. Beryllium has 2. Let's do it this way. There's 2 for beryllium. Oxygen, 6. 1, 2, 3, 4, 5, and 6. Doesn't really matter where. Good. And bromine, 7. 1, 2, 3, 4, 5, 6, 7. There we go. And does it really matter where these dots are? No. As long as you have 2, 6, 7 surrounding your symbol, and there's no more than 2 on a side in general. Got it? Perfecto. How are we doing on time? I think it's time to quit. See you next time.